In this video, we're going to do proposition 5.1.2, which is a very nice proposition about a special case where function f is continuous and can be factored. And we're going to do example 5.1.3, which demonstrates the use of this proposition. So let's start with 5.1.2 here. If f of x, y is continuous on a rectangle AB times CD, and in the special case that f can be factored as a function of x times a function of y, then the double integral over r of f of xy dA can be evaluated as the integral from a to b of g of x dx times the integral from c to d of h of y dy. So let's take a look as to why this is the case. So Fubini's theorem tells us that the double integral with respect to r of f of xy dA can be evaluated as an iterated integral over the rectangle because f is continuous. I can choose the order of integration, so I'm going to write it as the integral from c to d of the integral from a to b of f of x y, and this is going to be dx dy. Now, f of x, y can be factored as g of x times h of y. So let's do that. So that's the integral from c to d and from a to b of g of x, h of y, dx dy. Now, this first integral here, this first integral in red now, that integral is an integral with respect to x. So h of y is constant. I'm going to bring h of y outside of that first integral. I can't bring it outside of the second integral because the second integral is with respect to y. So I'll bring it in between the two, which means that I'm going to get here the integral from c to d of h of y times the integral from a to b of g of x dx times dy. Now I'm going to put some brackets here to remind us that that integral is being done here entirely first, and that integral is just going to give us some number as an answer. And that number, of course, is a constant with respect to y. So that number can be brought out again of the integral. So I'm going to bring this whole bracket outside, which is going to give me the integral from a to b of g of x dx. That's the whole integral that's been brought outside of the integral with respect to y, and then the integral with respect to y is from c to d of h of y dy, and what do you know? We have it. So there is the proposition. In a very special case where f can be factored, you can evaluate a double integral as the product of two single integrals. So let's go and do that in example 5.1.3. This says use proposition 5.1.2 to evaluate this double integral where r is the rectangle 0 to the root of ln 2 times 0 to the root of ln 3. All right, so to be able to do that, we have to say that our function f of xy factors. So let's let f of xy be this xy times e to the x squared plus y squared. Well, to see that this factors, I have to use a law of exponents to rewrite this as xy e to the x squared times e to the y squared, which means I can write this as x e to the x squared times y e to the y squared. So my function does indeed factor into a function of x and a function of y, which means that the double integral over r of x y e to the x squared plus y squared dA can be evaluated as the integral from 0 to the root of ln 2, the integral from 0 to the root of ln 3, of x, y, e to the x squared, and I'll write it times e to the y squared. Now I've got to get my order right. This inner integral was dy. The outer integral was dx, which means that I can go and write this. In fact, if I'm using proposition 5.1.2, and I've already shown that it can factors, I could jump directly to the product. That wasn't the product, this is the product. So I can write this as the integral from 0 to the root of ln 2. That was my x interval, so x e to the x squared dx times the integral from 0 to the root of ln 3 y e to the y squared dy. So those are two integrals that we have to evaluate using Cal 1 methods and Cal 2 methods. And Cal 2 methods here looks like a perfect substitution. So for the integral on the left, the x integral, I'm going to let u be x squared, which means that du is 2x dx, or 1/2 du is x dx. And when x is 0, well, u is still 0. And when x is the root of ln 2, then u is that squared, which is ln 2. So that means I am getting for the x integral, the integral from 0 to ln 2 of 1/2 e to the u du. And if I do a very, very similar thing on the other side, I would let v be equal to y squared, and I will get the same kind of situation. So the integral from 0 to ln 3 of 1/2 e to the, what are we getting here? E to the v times dv. These are both simple integrals now. So the 1/2 times 1/2, I'll bring those out to the front, times 1/4. I have e to the u, that's the antiderivative that I need, from 0 to ln 2, times e to the v from 0 to ln 3, which gives me 1/4, times e to the ln 2 is just 2, minus e to the 0 is 1. E to the ln 3 is 3, minus e to the 0 is 1. So 1/4 times 2 minus 1 is 1, times 3 minus 1 is 2. 2/4 is 1/2. So a very useful property that if your function factors, you can evaluate two single integrals and multiply them together instead of evaluating a iterated integral. And also a little reminder, this is a technique substitution that you would have used in your integral calculus course. We are starting to integrate now in our course, so all of the integral techniques, integration techniques that you saw before are probably worth reviewing as we go forward.